Welcome to Maths with EJD. This is me revisiting the idea of single points and the Frobenius method, which I had done before, but I think it's important to state clearly how to know singular points and to also know whether they are regular or irregular singular points. Let's go. Okay. A second, a second order, a second order linear ordinary differential equation has the form P of x y prime prime plus Q of x y prime plus R of x y equals 0. Okay. Um, so with this, we have that a point, at a point x equals x naught, at a point x equals x naught, it is singular, okay, if P of x naught is equal to 0. So we need to also know that singular points are classified. Singular points are classified as regular or irregular based on the behavior of the coefficients near x naught. Okay, so let's take them one after the other. Let's talk about regular singular points. Regular singular points. All right. So if P of x naught is equal to 0, but both, if P of x naught is equal to 0, that's already a singular point, right? But in addition to that, so once we have established that it's a singular point by knowing that P of x naught is equal to 0, but now both x minus x naught multiplied by Q of x over P of x and x minus x naught squared R of x all over P of x. This, right, actually remain analytic. Both of these remain analytic, or in another sense, we say they are both finite. They are defined, okay, at x naught. Then in that case, we say they are regular singular points. And if this condition fails, then they are irregular singular points. Okay, so talking about irregular singular points is just a negation of that. Irregular singular point. Okay, so if either expression above becomes infinite or undefined at x naught, then we have an irregular singular point. Okay, let's take some examples. Imagine this example now. So can we say it is to classify? Let's call this example 1 because we have more examples coming. So classify singular points. Classify the singular points of x squared y prime prime plus x y prime plus x minus 1y equals 0 at x naught equals 0. Something like this. So um here, right, we say that p of x is equal to x squared. That's this. Then q of x is equal to x. That's this. And then r of x is equal to x minus 1. X minus 1. That's this. So with that done, the next thing we want to check is okay. So with this, right, we can just say there is a singular point. There is a singular point at P. There is a singular point at x equals 0, since P of 0 will automatically be equal to, P of x is x squared, will be 0 squared, and that is 0. So since at 0, we have a singular point. So there's a singular point at x equals 0. Since P of 0, when you evaluate P of x at 0, you get 0. So it means that there's a singular point at x equals 0. Now, with that settled, then we can now look, so we want to check whether it is a regular or irregular singular point. So, um, so to check for regularity, we want to see whether it is a regular singular point or not. So to check for regularity, we have x minus x naught into q of x all over p of x. And that is equal to, since x naught is equal to 0, right? We have x minus 0 into q of x. Q of x is x. Then p of x is x squared. So we simply have x times x over x squared. And all of that is equal to 1. So this is, so if you substitute x equals 0 here, the value is always 1. So this is analytic. You can also say it is finite. That's another thing you can say. And because it is analytic or finite, so this condition is satisfied for regularity, then this is 1. The second thing we want to do is to do x minus x naught squared r of x all over p of x. Okay, that is x minus 0 squared. Then r of x is now x minus 1 all over x. Okay, that's p of x, right? So then we have x, so that's x squared times x minus 1 all over x. So this cancels one of this. So at the end of the day, we have x into x minus 1. And if you put 0 into that, the answer is 0. Okay? So even if you put 0 into that, you still get something reasonable. Okay? So with this now, okay, we can say, of course, this is equal to, I'll just do this in grid. At x equals 0, we have 0 into 0 minus 1, which is simply 0. 0 is a good answer as far as it is not infinity. So with this also, we say that this is also analytic. It is analytic. Of course, this was at x equals 0, right? This is also analytic at x equals 0 because you have this expression defined at that point. So with that done, we can say that since both are analytic, okay, you can say that x is equal to 0 is a regular singular point. Is a regular singular point. Okay. So if one of the two should fail, then it's not a regular singular point. So that's one example. Can we look at an irregular case? Let's look at an irregular case. Say example 2 now. Example 2, where we talk about an irregular case. So okay, consider now that we have x, y prime prime plus y prime plus y equals 0. So clearly here, p of x is equal to x, that's this. Q of x is equal to 1, that's the coefficient of y prime. Then r of x is also equal to 1, that's the coefficient of y, in front of y. All right. So with all of that now, so um, if we say at x equals 0, p of 0 is what? It's simply 0. And because of that, right? So we can, so we have a singular point. We have a singular point. We have a singular point at x equals 0. Settled. Next, we want to check for, so to check for regularity, what do? We have, of course, so the first thing we have is x minus x naught into q over x, q of x over p over x. That is x minus 0 into q of x, that's 1. P of x is x, so 1 over x. So this is x times 1 over x. And that is simply 1. That is analytic at x equals 0. So it's analytic there. Then secondly, we have x minus x naught squared q of x. Now r of x, right? So we have r of x all over p of x, and that is equal to x minus 0 squared times r of x is 1, p of x is x. So we have x squared times 1 over x. Okay, so this cancels one of this, and the result is x, which is also analytic. Okay, it is analytic. If you put 0 into x, you still get 0, so it's analytic. So with that done, right, then we can just simply say that we can say that um that x equals 0 is a regular singular point. Okay, is a regular singular point since the two conditions hold. Since the two conditions hold. Okay, I even said this was going to be a regular case. Well, maybe this is not appropriate yet. So let's just call it example 2. So let's now go for, say, example 3 now. Example 3. So example 3. In the case of example 3, imagine you have y prime prime plus 1 over x squared. In fact, okay, plus 1 over x squared y plus y equals 0, right? Plus y prime, that is. So here we have p of x is equal to 1. Q of x is equal to 1 over x squared. And r of x is also equal to 1. Okay? So, at x equals 0, you see that p of 0 will be 1. So that means that this is not equal to 0. So we can say that it is not a regular singular point. Okay? It is not a so there's no singular point, rather. There's no singular point at x equals 0. But then this value of q should tell us something. Okay. So that should tell us something. So near x is equal to 0. So we see that q of x, which is 1 over x squared, will be approximately 1 over 0 squared, which is infinity. So near x equals 0. So near x equals 0, q of x blows up faster, it blows up faster. That means it goes to infinity very fast than a regular singularity, allows, suggesting irregularity, suggesting irregularity if formulated. Okay. All right. So, I mean, with all of that out of the way, so basically, you know the trick. You have a question, identify P of X, Q of X, and R of X. Then check for, it doesn't have to be only zero. Maybe it is X equals zero, X equals one, or X anything. So as far as you put that in and you get zero for P of that value you're evaluating, which is mostly zero, is also zero. Then you have a regular singular point. Then you can now go ahead and use these two conditions to establish whether they are regular or irregular singular points. Okay. So at the end of this whole thing, I'm going to give uh, practice questions that you can play with a lot. Okay, so let's go for Frobenius method, which you have done before, by the way. I just want to emphasize it again. Frobenius method. So we say that for a regular singular point, so once you establish that what you have is a regular singular point, for a regular singular point at x equals 0, mostly, so assume a solution, y equals summation from n equals 0 to infinity of an x raised to power n plus r. Okay, this is the solution you assume generally since we're looking for series solution. So here we say where r is determined, where r is determined by the indicial equation. We've done this before, by the indicial equation. I'm just bringing more clarity here, by the indicial equation. So the next thing we want to do is to now substitute. So we substitute into the ODE, okay? Then we shift indices. So substitute into the ODE, shift indices, substitute into the ODE. Then you shift indices. And after shifting indices, then you solve for R. Solve for R. That's the next thing you do. And then number 4, you solve for coefficients AN. Solve for coefficients AN. So those are the things involved, the steps involved in this situation. All right, so let's take an example, another example again. So imagine example 3 of maybe 4 now, right? Did I number the previous ones? I did not. Okay, yeah, it's example 4 now. So example 4 is about Frobenius. So we need to solve xy prime prime plus y equals 0. Obviously, you can see that it is of the standard form we've been talking about. So we see that if you rewrite it in the standard form, this is more like xy prime prime plus 0y prime plus 1y equals 0. So that simply tells us that p of x is equal to x, r of x is equal to 0, and no, p of x is 0, right? Q of x is 0, q of x is 0, and r of x is equal to 1. Okay, so that we can now have this. So we see that at x equals 0, we have p of 0 equals 0. So there is a singular point, as a singular point at x equals 0. Now, with that done, then we can go for the other one. So, to check for regularity, like we've been doing, to check for regularity, to check for regularity. Again, of course, x is 0, so we can just go straight, right? So we have x, the first thing we do is x, r of x, all over p of x, okay? So that is x times 0 all over x again, because p of x is x. So everything is just simply 0. So in that case, we say it is analytic. It is analytic, at least it is defined, so it is analytic, or we say it is defined. 2, we have x squared. Oh, this is q of x, sorry. q of x Q of x is 0, not r of x. Yeah. So x squared r of x all over p of x. So that is x squared times r of x now is 1, then p of x is x. So we have x again. So even if you put 0 into this, it's still reasonable. So this is also analytic. Okay. So since this is analytic now, we can use the so x equals 0 is a regular singular point. Is a regular singular point. Okay. So singular point is when you have p of the value to be equal to 0, and then regular singular point is if these two conditions are analytic. Okay. So with this done now, um, since the since the point x equals 0 is a regular singular point, we can solve the ODE with Frobenius method. Okay. In that case, what we'll then have to do is to say that so we assume, right? We assume y equals summation from n equals 0 to infinity an x raised to power n plus r. Okay, and then we have y prime, which we need because we need the second derivative, so we need to get through this. So we have an, then n plus r, x raised to power n plus r minus 1. Then we have y prime prime equals summation from n equals 0 to infinity an into n plus r into n plus r minus 1, x raised to power n plus r minus 2, x raised to power n plus r minus 2. Okay. So what we then do is we substituting, we started with xy prime prime plus y equals 0. So that means that is x summation from n equals 0 to infinity of an n plus r minus 1 into n plus, that's n plus r into n plus r minus 1, then x raised to power n plus r minus 2. Yep. Yeah, that's what we have here. And then for y, that's summation from n equals 0 to infinity of an x raised to power n plus r. And all of this is equal to 0. Now, with that in place now, we can, okay, we can even tidy this up. We just push the x inside. So we have summation from n equals 0 to infinity, or let me change the color, right? So we have now summation from n equals 0 to infinity an n plus r minus 1, then x raised to power n plus r minus 1 plus summation from n equals 0 to infinity an x raised to power n plus r equals 0. So at this point, you discover that the power of x are not the same. So we have to find a way of making them the same. That is where the shifting of indices actually come in. Okay, so what we now have to do is so we have to shift, we have to shift the indices, shift the indices, or better still, shift the index. Let's shift the index of the first term, shift the index of the first term to be x raised to power n plus r minus 1 or something, or to make it balanced up. So let me not specify this now. Shift the indices of the first term, right? So that it can match up. But then, but first for this initial equation, but first obtain first, but first obtain the initial equation, for the for the lowest for the lowest index, and that is where n is equal to 0 on the left hand side. Now you can see n plus r minus 1 is lower than n plus r, so the lowest index is going to be from, okay, maybe I guess I have to rewrite that, right? So we have summation from n equals 0 to infinity of an into n plus r into n plus r minus 1, then an, oh, okay, it's only one in it. So x raised by n plus r minus 1 plus summation from n equals 0 to infinity for an x raised by n plus r. So an x raised by n plus r equals 0. Okay. Now, because this power is lower than this now, so the initial equation is going to come from this first term. So we just say, so when n is equal to 0, so we have a0, okay, into a0 into 0 plus r, okay, into another 0 plus r minus 1, okay, then x raised to power 0 plus r minus 1. Then we now continue plus summation from n equals 0. Now we've taken out that, so we have n equals 1 to infinity, right? Then we have an into n plus r into n plus r minus 1, x raised by n plus r minus 1. Okay, then I can bring this one now. So summation from n equals 0 to infinity of an x raised by n plus r equals 0. Okay, so we don't have to worry about this one because the power is obviously lower. So here now we can tidy this up, and we have on this side we have a naught r into r minus 1 x raised to power r minus 1. So because it has the lowest power, it's automatically going to give us our initial equation. Okay, but of course we still write the whole thing first. So that would be summation from n equals 1 to infinity an n plus r minus 1 x raised by n plus r minus 1 k plus summation from n equals 0 to infinity an x raised by n plus r equals 0. Now with this, we now have to shift. So uh to shift the index of the middle term So the middle term is just this one now. We want to make it n plus r, like this one is n plus r. And the only way to do that is, or want to at least make it something plus r. So, and the way to do that is we have to make n minus n into something, okay? So we now say let n minus 1 be equal to k. So that way we can have that to be k plus r, so which is still balance up. So if n plus 1 is equal to k, so it simply means that so this implies that when you have n equals 1, now, so it means, of course, this is going to be n equals k plus 1, right? So n is equal to k plus 1. So that simply means that n is equal to 1 is the same thing as k plus 1, all right, equals 1. which means that k is equal to 1 minus 1, and that means that k is equal to 0. So it means if you say n minus 1 equals k, so it means you are resetting this one to start from k equals 0 to infinity. So we are going to do all that k replacement now. So we have that first part, 0 not r into r minus 1, okay? Then x raised by r minus 1 plus summation from k now equals 0 to infinity, because anywhere you see n minus 1, you put k. So, and anywhere you see, then n itself, anywhere you see n minus 1, you put k, or anywhere you see n, you put k plus 1. Okay, that's the implication. So we have, so this will now be a k plus 1. An now becomes a k plus 1. Then n plus r is k plus r, uh n is k plus, so that's k plus r plus 1. Okay, so this will be k plus r plus 1. If you look at this here now, because n is now k plus 1, that's k plus r plus 1. Then n minus 1, of course, n again is k plus 1, so k plus 1 minus 1, so that would just be k plus r here. So we have k plus r for k plus r for this now. So we now have x raised to power k plus r again, because n minus 1 is k. So that will be x raised to power k plus r. Okay, so that has balanced up. And then when we come down here, since the power will now be like the same now for any particular k we have, then we are good to go. So this will now be summation from n equals 0 to infinity of summation n equals 0 to infinity of an x raised to power n plus r, and all of this is equal to 0. Okay. So since we have changed that to k, right? I think we can also take the liberty to make this one into k also. So for the sake of consistency, we are not touching this. We are just resetting, right? We are just resetting the first one. So because definitely means the same thing. So this is now uh k. So anyway you see n, let me just rewrite the whole thing. Okay. So that's summation from k equals 0, k equals 0 to infinity of that part now. So ak x raised by k plus r. So this is ak x raised by k plus r equals 0. And with this in place now, we need to find the initial equation. So the initial equation is all this coefficient now will be, because the lowest power here is r minus 1. So all of this now, we have a naught r into r minus 1 equals 0. And of course, a naught has to be not equal to 1. So that implies that the initial equation is r into r minus 1 equals 0. And that also implies that it means r is equal to 0 and r is equal to 1. So these are the values of r. So with these values of r, now we can now go back to the original expression and deal with that. Okay. So at this point, we can switch gears, and then so we can say that we can have two cases. So we have case 1. So for case 1, r is equal to 0. Case 1, r is equal to 0. So in that case, we can come back to this remaining expression now. Since every k plus r is common, so we now have and r is 0, right? So we have summation from k equals 0 to infinity. We just put everything together. Then we have ak plus 1. We can have k plus r into k plus r plus 1. I'm just rearranging, right? So this is k plus r plus 1. Then ak plus 1. We have that. and then we have AK alone. So that's like plus AK down there, AK. Then x raised to power k plus r is common now. So all this into x raised to power k plus r equals 0. Okay. So, all right. So case one is r is where r is 0, right? So it means that um mm, I've said it already, but let me just go. So for r equals 0 now, we can then have summation from k equals 0 to infinity of I'll just go straight. So r is 0, so we have k. All right, we have k into k plus 1, like this, k into k plus 1. And then this is a k plus 1 plus ak. All right, so that's k into k plus 1, then ak plus 1 plus ak. And r is 0, right? So that is x raised to power k equals 0. So, of course, from what we've known, this whole thing have got to be 0 for us to get what we need to get here. So we can now say, so k into k plus 1, ak plus 1 plus ak is equal to 0. So that's how we can get a recursion formula. So we have k into k plus 1, ak plus 1 equals ak. All right? That's minus ak for that matter. So that's ak plus 1 is equal to minus 1 over k into k plus 1 multiplied by ak. So this is one recursion formula we can have, and then we can get some terms out of this. So let's go. At k equals 0, so we can get like not, right? So at k equals 0, so it means we have a1 equals minus 1 all over k itself is 0. Okay, k equals 0 would most likely not work here because it will just cancel out this expression. So it means k equals 0 is not going to work. Let's forget about that. So we have to start from k equals 1. So at k equals 1 now, so we have a2 equals 1 minus 1 all over k is 1. So 1 into 1 plus 1, that's 2. Then a1, okay? So that is a2 equals minus 1 over 2 a1. So we have a2 right here in terms of a1. Then we can go for k equals to what? K equals 2. That will be a3, right? A3, equals minus 1 all over 2 times 3. That's 2 into 3. Then we have a2, right? That's a2. Interestingly, we have a2 up there. So this is a3 equals minus 1 over 6 into a2, which is minus 1 over 2 a1. All right. And so it means that a3 is equal to 1 over 12 a1. So we have that. Then we go for at k equals 3. At k equals 3 now. So we have a4 will be equal to minus 1 over 3 times 4. That's 3, 4. Then a3, right? That's a3 because k equals 3 now. So that means that a4 is equal to minus 1 over 12 into a3, which is now 1 over 12 a1. So we have a4 to be equal to minus 1 over 144 a1. Okay? And we have this. So with this now, we can go back to the original expression. We can go back to where we started from since we now have all these things. So we now say, uh, therefore, y, which is summation from, we can even go back to n equals 0, an x raised to power n plus r. Okay, we can use this now. So that means we have y is equal to a naught x raised to power x naught, okay, plus a1 x raised to power x, okay, xr, right? Yeah, because n is 0. So xr plus a1 x raised to power r plus 1 plus a2 x raised to power, we got up to a4, right? X raised to power r plus 2, okay? Plus a3 x raised to power r plus 3 plus a4 x raised to power r plus 4 and all the rest. So we can just fix up the value. So y here is equal to a naught. Let's take so take a naught to be 0. Take a naught to be 0. So that means that we have 0xr plus a1 now. Okay, we have a1 in terms of the rest. So a1 x raised to power. Of course, we already know that r is equal to 0 in this case. So r is 0. So that means that we have, in fact, this is also 0 here. So this is 0. R is 0 already. So that's a1 x raised to power 1 because r is 0, then plus a2 now. Okay, that's where we begin to have things. So a2 is minus half a1. So that's minus half a1 x raised to power 2. Then a3 is 1 over 12 a1. a3 is 1 over 12 a1 x raised to power 3 plus a4. a4 is minus 1 over 44 minus 1 over 144 a1 plus all that. So we can have this. So y now is simply a1x minus half a1 x squared plus 1 over 12 a1 x cubed minus 1 over 44 a1 x raised to power 4. And that continues. So we can call this y1 if you like, So let's call this y1 because we are going to have another case. So y1 of x is simply the same thing as a1 is common everywhere. So we have a1 into x minus half x squared plus 1 over 12 x raised to power 3, then minus 1 over 44, minus 1 over 144 rather, x raised to power 4, plus all that. So that's the first expression for the first case. Okay? For the first case, that's all we have. Now, let's switch gears for the second one. So now, imagine that you have the second case where, so for case 2 where for the initial equation, right, we got r to be 0 and r equals 1. So we go for case 2. So case 2, r is equal to 1. Okay, case 2, r is equal to 1. And okay, so again, we go back to the expression again. So we go back to when r is equal to 1, we go back to this original, this k plus 1 something. So we can say that from summation from k equals 0 to infinity of, do I still remember what that is? So that is k into k plus 1, a k plus 1. Okay, k into k plus 1, ak plus 1 plus ak, all right? And then r is equal to 1, right? That's also another difference. So this is x raised to power k. Where did the r thing come in? Okay, yeah, I get it now. So this is the original thing. So r is now equal to 1. So we have x raised to power k plus 1. Okay. So this is now x raised to power k plus 1, and this is equal to 0. So now again we just equate this again to 0. What's the difference here? Okay, I think I have skipped something. So we should come to this original place. Yes. I should come to that original place. I was wondering what was happening. Okay, so let's do the original thing. So we go back to the main thing. This is what we have. So k plus r plus 1. Okay, so k plus r, k plus r plus 1, a, then ak from up here. So it's AK plus 1. Has it always been AK plus 1? Yes, I think it is. So it's AK plus 1. Okay. AK plus 1 plus AK. X raised power K plus R. Okay. AK plus 1 plus AK. Then X raised power K plus R equals 0. Okay. So at R equals 1 now, and then we have summation from K equals 0 to infinity of, so this is now K plus 1, then K plus 2, because R is 1 now, into A, K plus 1. Okay, that remains K plus 1, then AK, then X raised power K plus 1, because R is now 1, equals 0. So again, we just equate that to 0. So we say again, for the recursive equation, we have K plus 1 into K plus 2, AK plus 1 plus AK equals 0. Okay, that's what we should have for that. So that, in short, AK plus 1 is equal to minus 1 over, that will be equal to minus 1 over K plus 1, K plus 2, AK. All right. So we have this expression. So we can now go one after the other now. So we can get not. So at K equals 0. So we have A naught, right? So we get A1 rather equals minus 1 over, because K is 0 now. So this is 1 into 2, then A naught. Okay. So we simply know that A1 is equal to minus 1 over 2 A naught. We keep that. And the next thing, at K equals 1. So we go there again. So that is A2. A2 is now minus 1 over 2 plus 1, 3. 2 plus 2, 4. All right. Then A2. So we have A2. So this is A2. Oh, really? Not A2. That should be A1, right? So that's A1. Yeah, this should be A1 because K is 1. This is A1. So A2 now is minus 1 over 12, A1. So this is A2 equals minus 1 over 12 into A1 is already minus half A naught, minus half A naught. So A2 is equal to minus 1 over 24 A naught. So let me just go one more step and take at K equals 2 now. At K equals 2. So we have A3, I believe, into minus 1 over 3 plus 1 is 4. 3 plus 2 is 5, I believe. Yeah, because we have K plus 1. Yeah, 3 plus 1, 4. 3 plus 2, 5. Like that. Then we have A2. So this is A3 equals minus 1 over 20 into A2. Then this is A3, which is equal to minus 1 over 20 into minus 1 over 24. Minus 1 over 24 A naught, like that. And then lastly, that is A3 equals 480, I think. So that's 1 over 480 A naught. All right. So now we are going to get the second Y. Therefore, Y2 of X again, we can even go from the beginning. So summation from n equals 0 to infinity of an X raised to power n plus R. And then we expand. So we have A naught on the rest. So Y3 of X is Y2 of X rather, sorry. Y2 of X is equal to A naught X raised to power n plus 1, right? Because R is 1 in this case. A naught X raised to power n plus 1 plus A2 X raised to power n plus 2. No, what are we doing here? Okay, let me go back. So don't forget, right, that uh R is equal to 1 here, okay? So as we go with the ends, we can flow along. So R is 1 constant. So we have in fact, maybe I should put the R directly because R is already 1. So there's no point stressing over that. So this is plus 1 because R is 1 straight. So now we just focus on the end. So we have A naught x raised to power 1 plus a1 x raised to power 2 plus a2 x raised to power 3 plus a3 x raised to power 4. Okay, we have as much as a3, so we are good. So we have all this here, so we can just fix that up. So y2 of x is equal to a naught is, we actually have a proper a naught now, so we have a naught, so we just leave it like that. So we have a naught x, okay, plus a1 here is minus half a naught, so that is minus 1 over 2 a naught, plus a2 is oh, this should be plus 1 over 24. Yeah, a2 is plus 1 over 24. Yes. So that here, this will now be minus 480. So this is plus 1 over 24 a naught. So 1 over 24 a naught. Then a3 is minus 1 over 480, minus 1 over 480 a naught. And that goes on. So I can just bring out the a naught at once, so that y2 of x is equal to a naught into x minus half. Oh, I forgot to put all the x's. So this is x squared, x cubed, x4, and so on. So half x squared plus 1 over 24 x cubed minus 1 over 480 x raised to power 4, and all of that continues. So we have that. So finally, you can say, therefore, the overall solution is y. The overall solution is equal to y of x, which is equal to y1 of x plus y2 of x. Okay, and that means that we have y of x to be equal to, for the first part, that y1 of x, that's a1 into x minus half x squared, a1, or we can even start with this one since it's a naught. Yeah, anyone that comes first is fine. So we have a naught into x minus half x squared, all right? Plus 1 over 24 x cubed, and so on and so forth. Okay, plus the other one, a1 into, I'll just pick the first three, x minus half x squared plus half x cubed. X. Oh, that also started with x. Interesting. Yeah. Okay, x minus half x squared plus half x cubed. X minus half x squared plus half plus 1 over 12 x cubed. And that goes on like that. So that's what we get for that. It's really a tedious process. Yeah, so we have this, right? So with this in place, we are good to go. Yeah, let me just take some practice questions. It's been a long one already. So practice. I think I'll just go with 3. So question 1. For the ODE, x squared y prime prime plus 3x y prime plus x plus 1 y equals 0. Okay. Identify and classify the regular singular point at x equals 0. Okay. Then question 2. Okay, I guess 2 will be good. So for x squared y prime prime minus x y prime, okay, plus Okay, let me do this other one. Okay, let me change it to this. Solve 2x squared y prime prime plus x y prime plus x minus 1 y equals 0 near x equals 0 using Frobenius. Using Frobenius, compute the initial roots. So just like in the case we just did, the initial roots are 0 and 1. Compute the initial roots and the recurrence relation. The recurrence relations are the an plus 1 and all the rest. And the recurrence relation will not be an plus 1 in this case. Just follow what you get. Okay, so let me know your answer in the comment section, either on Facebook or on YouTube. Also, indicate how helpful these videos are for you. And let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then if you have subscribed to this channel, thank you for that. If you have not, please go ahead and subscribe because there's more to come. After this video, I'll be talking about systems of differential equations, and that's going to be really interesting. So you don't want to miss out on any of that. So subscribe to the channel, hit the notification bell so you can always get alerted anytime a new video is released. And don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.